All right, in this lesson we will start to look at some properties of graphs of rational functions. You know that rational functions cannot be defined, they're undefined when the denominator is 0. So we've already talked about this, but of course you know that, for instance, in this function right here, the denominator would be 0 if x was -3. So x can't be -3. It's a spot where the graph is undefined. Okay? Here, if this is 1, it would be undefined. If this is -4, it would be undefined. So the graph is undefined at -1, or at +1 or -4. And here, of course, x can't be 0, or the denominator would be 0, so it's undefined at 0. Now, there's different ways of being undefined. Okay? They have, when a graph is undefined, there's some sort of break in their continuity, meaning you can't make the graph without lifting up your pencil. So there's different ways this can show up. One of the ways this can show up is a graph that looks something like this. Okay? I can't draw this entire graph without lifting up my pencil. I can draw the top branch, but then I would have to lift up my pencil to draw the bottom branch. Okay? So that means that there is some discontinuity in here. One of the ways that discontinuity shows up is that you might have a vertical asymptote. That's a vertical line that shows up as a spot where the graph is undefined. On this particular graph, this line right here is a vertical asymptote. And what that means is the branches approach that line and get closer and closer and closer and closer and closer to that line as they get higher, but it never ever touches that line. Same thing on the bottom. This branch would get closer and closer and closer and closer and closer to that y-axis, which is a vertical asymptote in this case, but it will never touch it. Okay? You figure out where those vertical asymptotes are by factoring them and looking at the factors that remain in the denominator. And that'll make more sense when we kind of do it, but that's how it works. Okay? Then there are horizontal asymptotes. A horizontal asymptote is very similar, except for it's a horizontal line that a graph would approach. So this line right here, which happens to be the x-axis in this case, but it's not always the x-axis, is a horizontal line. Because again, that branch approaches that horizontal line, but never ever ever touches it. Same thing here, the graph approaches that horizontal line but never touches it. So that would be a horizontal asymptote. Those need to be sort of figured out using your calculator and using your table. They're a little bit trickier, but we'll show you how to do that eventually. Okay, and then there's points of what are called removable discontinuity, where there's literally like a hole in the graph. And you figure out those by factoring and then looking at whatever factors cancel. Whatever factors cancel give you the points of removable discontinuity. And how that shows up in a graph is when you go to make the graph, which we aren't going to do in this video lesson, we will do it in the next one, but there's literally a hole. There's literally going to be a spot, let's say right here, where the graph does not have a specific value. So it's like just one little spot that's a hole. Not an asymptote, not a line that it approaches, but it's a hole. Okay? And that's a point of removable discontinuity. So those are some ways that discontinuity shows up. They show up as vertical asymptotes, horizontal asymptotes, or a point of removable discontinuity. All right, so how do we deal with this algebraically? Well, here is a function here, a rational function, and the first thing you want to do is you want to be able to factor it. So on this top one, I will factor x squared minus 1. You know it's a perfect square, so it factors as x plus 1 and x minus 1. And then on the bottom, that factors as x and x. 5 can be only 1 times 5. If it's a plus at the end, you know it either needs to be plus, plus, or minus, minus. Because of that minus in the middle, that's how that looks. Okay? Then you're going to look at what can cancel. So I can cancel an x minus 1 and an x minus 1. And because those canceled, and if you think about setting it equal to 0, then when they cancel, that x equals 0, or sorry, not x equals 0, x equals 1, x minus 1 equals 0, so x equals 1. The part that cancels gives you your point of removable discontinuity. Okay, so all you need to tell me is x minus 1, and then right here next to it, write removable discontinuity, so that I know. When you go to graph that, which we won't do in this lesson, but when you go to graph that, that means there's going to be a hole in your graph where x is 1. Okay? All right, and then you're going to look at what factors remain in the denominator. So in the denominator in this case, this is the factor that remains. Of course, if I set it equal to 0, I would get x equals 5. And the factors that remain in the denominator tell you where your vertical asymptotes are, or those vertical lines that the graph will approach but never touch. Okay, so that gives you a vertical asymptote because it's where it remains. So that's all we need to worry about algebraically right now. We'll do one more just to make sure you're okay here. Again, you can factor the top. The top will factor as a perfect square, x minus 2 and x plus 2. And the bottom will factor as x and x, 2 and 3, or it could be 1 and 6, but it is going to be 2 and 3 here. So that's how the bottom factors. And then, of course, look at what cancels. In this case, an x plus 2 will cancel here with an x plus 2. And again, the points that cancel give you your points of removable discontinuity. So if I set x plus 2 equal to 0, that means I get x equals negative 2. And that gives you my point of removable discontinuity. And then I want to look at where my vertical asymptotes are. And my vertical asymptotes come from the spots where your graph, where the factors remain in the denominator. So I have a factor that remains right here of x plus 3. When I set that equal to 0, I get x equals negative 3. And again, that gives you your vertical asymptote. Okay? And that's all we need to know for now. We'll learn to graph them in the next lesson.